yeah, we can do all this math, and in a moment we're going to use this basic mathematics to master subnetting, but why are we doing this? This reminds me a lot of the OSI model, right? Where we had to stop and say, why are we studying this? What's the deal? Why are we being tortured with this material? Or in that same situation now with subnetting, we look at this and we go, why are we doing this? Well, that's what I'm most interested in teaching you today, really. Why are we doing this? Let's go ahead and talk about why we are going through this critical exercise of TCP/IP subnetting. One of the things that we know is that a flat network topology simply will not work for us. Yeah, when we try and put all of the machines in one flat network, it's just not going to work for us. Imagine at your corporate headquarters, you have 2,000 employees. Each of those employees has a voice over IP telephone and a personal computer and an iPad, let's say. Lucky them. And each of these individuals has all three of these devices. All three of these devices for each individual needs the IP connectivity. That is 2,000 times 3. That's 6,000 devices that all need to be on the network. If we put them in one subnet, in one TCP/IP subnet, we would have pure chaos. Just from a broadcast perspective, all of those devices would hear all of the other devices' broadcasts. As a matter of fact, Cisco tells us that when we reach about 500 machines in one flat network segment, we are going to start to get communications issues. So we always target 500 or fewer machines, hopefully like half that number, like 250 machines in a particular subnet, and then we start to shy away from putting more machines into that subnet. By the way, here for his take on these issues with flat topologies is our good friend and our guest expert for this class, Doug Bassett. Doug, take it away.
You ever live in a house that had a whole bunch of teenagers and only one phone, but every teenager had their own extension? Well, every time you pick up the phone, somebody else is chattering away. Get off the phone! Get off the phone! And they're yelling back at you, and before you know it, nobody can communicate. Well, that's what a flat network topology is. We're all hooked together in hubs, which means there's really not a whole lot of traffic control. We use something called CSMA-CD, where you're essentially listening to see if anybody's talking. Oh, is any teenager on the phone? And if they're not, then you start talking, but you're still listening, and then all of a sudden you have collisions, and then everybody starts shutting up and backing off, and it's just a mess. So dealing with a flat topology has some very serious problems. Number one, you only have shared bandwidth, which means if I have a 100 megabit network, which sounds, 100 megabit, what the heck? But if I have 500 machines on there, they're each taking a slice of that, I really don't have much available bandwidth. And if Susan from accounting is downloading this big package from the internet, everybody has to listen to those packets going by, and while Susan's downloading them, nobody else can communicate. I mean, it becomes a huge, huge mess. Also, it's in the same broadcast domain. That means if this application that Susan just downloaded from the internet happened to be, a virus, and it starts freaking her machine out, her machine's broadcasting, hey, here's some packets, hey, here's some packets, hey, here's some packets. Everybody's machine has to hear that, has to actually process it, even if it's just to throw it away. It's like somebody backing up a garbage truck and dumping it in your living room. You have to scoop it up and throw it away. Same thing with all those bad packets. And if you're in the same broadcast domain, anybody can back up a garbage truck and you're off grabbing plastic bags. Also, since everybody is in the network, everybody hears everybody else. So try to have a security policy. You know, couple sniffers plugged into the network, hearing all the bit of traffic. You're trying to isolate stuff. I can find out what your MAC address is. I can change this. I can do that. It's really a huge pain. So how do you take care of it? Well, with your boss's approval, you go in and you find all of the hubs. You can usually tell because they're covered in dust. They're probably beige. They're very, very old, and they say hub on the front of them. You take them and you throw them away and put in switches. Switches are the sweet nectar of teenagers moving out of the house and giving you your own phone, or wiring separate phone systems just for them. So even though they're physically there, you don't have to listen to their chatter. Same thing with a switch. You're going into a tiered environment. And, you know, the whole idea here is to be able to gain access to the network, which is pretty much impossible in a flat environment. If you have more than about 5 or 10 machines and you're using a flat topology, your network is really a hurting unit. So do yourself a favor, find all those nasty hubs, swap them out with switches, and enjoy the sweet bliss of isolated networks.
Now, keep in mind that we got to refine what Doug said a little bit. Doug was talking about hubs, and they're certainly evil, but let's refine what Doug said a little bit there. It's not just taking all the hubs and replacing them with switches. That's not going to do it. We need to replace the hubs with switches and add routers, don't we? Yeah. You see, we could go ahead and just use switches, layer 2 switches, and connect them all together, but now our network is still considered flat because, again, everybody's in the same TCP subnet. Let me get out of the way here and show you what we need to do. Sure, get rid of all the hubs, but go ahead and add a router. There we go. Now we have different TCP/IP subnets. And guess what, folks? We just created broadcast domains. Look at this. This down here is one TCP/IP subnet, and the broadcasts stay in that domain. The router will not forward the broadcasts. Finance Subnetwork 3 is a TCP/IP subnet. It is its own broadcast domain. Broadcasts are filtered by the router. And then we have Engineering Subnetwork 1. Same thing. It's its own TCP/IP subnet. Look at the WAN interface. It's its own TCP/IP subnet. So our network just went from flat to not flat. Yeah. Some would call it now hierarchical, but let's just call it not flat. And now we start to really, really achieve benefits. And now you're starting to see subnetting, right? You can take one IP address and you can subnet that IP address into what we call different subnetworks. And this is exactly why subnetting is so incredibly powerful. And this is why we have to have a subnet mask. Yeah, we've been really focusing on IP addresses in this course, but we haven't focused yet, and we will starting now, on the subnet mask. The subnet mask simply tells the device how many bits of those 32 bits represent the host identifier portion and how many represent the network portion of that address. My analogy here is a simple one. It is the network is the street name and the host portion is the house identifier on that street. I was born at 10 Jones Street in Worcester, Massachusetts. So I was born at 10 Jones Street. The 10 is the host identifier. And what street did I live on? I lived on Jones Street. So there is this subnet mask's important job of telling us exactly how many bits represent the network portion and how many bits represent the host portion. Remember, the subnet mask utilizes ones to represent the network portion and zeros to represent the host portion. So it's just so incredibly awesome that we are able to apply this subnet mask to the infrastructure and divide up the network into these different subnets. Wow. Here's a look at how it works. Our mask is 255.255.255.0. This means we have 16, we have 24 ones in a row, and then we have 8 zeros. The first 3 octets identify the street address, and the last octet identifies the host ID. Here we have the 10.1.1 subnet. Here we have the 10.1.3 subnet. Here we have the 10.1.2 subnet. We've got switches to create our multiple collision domains. We've got routers to create our multiple broadcast domains, and things are just beautifully efficient. The routers end up being places at which we can apply security mechanisms like access control lists and sophisticated security techniques like that. So the routers are going to use these subnet masks to identify what particular portion of the IP address represents this important street address portion. We're going to go in and we're going to use the IP address and subnet mask in order to build the routing table and to know what portions of these addresses are street address identifiers. Remember, the subnet masks are ones identifying the network portion of the address. So when you look at a subnet mask, you can have a 0 in that field, you can have a 128 in that field, or a 192 in that field, or a 224 in that field, or a 240, or a 248, or a 252, or a 254, or a 255. These are the possible values for the subnet mask. Let me just put 0 up at the top here, since obviously it's a possible value in an octet in a subnet mask. This particular sequence is important, and a lot of students like to put this on their scratch paper as well when they are in the exam environment. Yeah, they like to list out these possible decimal values in a subnet mask octet when they're in their exam environment. Let's go ahead now and take a look at the default subnet masks for those address classes that we spoke about. And Bruce just gave us a thumbs up. So Bruce is saying, yeah, this is another tool that I list on my scratch paper. Bruce took the composite exam for CCNA, the brutally difficult ICND 1 and 2 composite exam, and Bruce aced his subnetting questions, all of them. Bruce, I believe you got 100% in that section, did you not? I believe you got a perfect score in that section. So Bruce is certainly going to be someone that we listen to. Yes, he did. He is certainly going to be someone that we listen to when it comes to advice on solving the subnetting requirements in the exam environment. And keep in mind, it will be even easier in ICND 1. All right, so let's look at those default subnet masks now. For a Class A address, and an example of a Class A address is the 10.x address, here we can see that address in binary. And then here is the mask, the default mask in binary. Notice the first 8 bit positions are all ones. Yeah, sure enough, this means that the default subnet mask for a Class A is 255.0.0.0. The first 8 bits by default in a Class A address identify the network, and the last 24 bits identify the host on that network. Now, writing out 255.0.0.0 every time you write out the mask, the default mask for a Class A, can be pretty annoying. So there is a shorthand for representing masks, and that is just to show the number of bits and a slash notation that make up the network portion. This is called prefix notation, and it is really pretty cool. Yeah, it's pretty darn cool, and we could go ahead and utilize this shorthand if we wanted to. And that was weird. I just lost my connection to my room for a moment. Let me just make sure everything is cool on my connection. Yeah, it appears to be. Okay. All right, so that's the Class A. And I don't see any questions there. Great job, everybody. Now let's go ahead and let's take a look at the Class B. Well, first of all, an example of a Class B. Hey, 172.16. Notice how they're using all private addresses here in the examples. That's just purely for illustrative purposes. This would work with non-private addresses too, of course. All right, there's the address in binary. Woohoo, that looks fancy. And look at this. This is what we care about here. There is the mask in binary and the mask in decimal. You're probably not surprised to learn that the first 16 bits are now representing the network portion. The last 16 bits are representing the host portion. And when we want to demonstrate this in the shorthand notation, we do our /16. Yep, our /16 will be the way we represent this in the shorthand notation. Next up, a Class C. No big surprise here. The first 24 bits are representing the network by default. The default mask, 255.255.255.0, and we have the prefix notation of /24. So, when we subnet. And your concern in CCNA studies is subnetting a Class C. That's right, because at the CCNA level, we are concerned about small networks. And Class Cs are appropriate for small networks. So when we subnet, we take one of these addresses and we extend the mask. We do what's called borrow bits from the host portion. We're going to take some of these bits and we are going to turn them on from a subnet mask perspective. Let's say we do 3 of them, and these 3 bits are now called our subnet bits, and they allow us to identify additional networks. Obviously, we're no longer going to have a 0 in the subnet mask. In fact, we'll have a 128 plus 64 plus 32 there in that particular position. And that is 224. So if we borrow 3 bits to create these additional subnets, we'll have a mask of 255, 255, 255, 224. And now we can create these additional subnets. But subnetting comes at a cost. Obviously, if we borrow bits to create additional networks, then we are stealing bits that could be used to identify hosts. Yeah, take a look at this. Here we see an important formula. The formula is 2 raised to the S, where S is the subnet bits. If we borrow 1 bit, we can do 2 raised to the 1 bit. We can create 2 additional subnets. So 2 raised to the S power is how many additional subnets we can create. The next formula that we want to take a look at is the host bits. 2 raised to the remaining host bits minus 2 gives us how many hosts that we could accommodate. So 2 raised to the 7th is 128, minus 2 is 126. So we can accommodate 126 hosts on each of these 2 subnetworks that we could create. Wow. So the formula of 2 raised to the S power gives us the number of subnets that we can create. The formula of 2 raised to the H minus 2 gives us the number of hosts that we can accommodate. Why the minus 2? Well, because we cannot have a host portion of all zeros, and we cannot have a host portion of all ones. The all ones host portion is reserved for broadcasting, and the all zeros host portion is reserved to describe that street itself. Great job, George, saying, yeah, we can't use 255 or 0, if you will, Just be careful, George, because notice if we only have 7 bits left for hosts, then, it's not 255, right? But I think you and I are on the same page. We can't have all zeros for your host bits. You can't have all ones for your host bits. I think that's the most accurate way to talk about this. You can't have all zeros. You can't have all ones. Because think about it. You could have, for your subnet bits, you could have 1, 0, 1 as your subnet bits. And then you can't have 1, 1, 1, 1, 1. You cannot have all ones here in the host bits. Now notice when you convert this whole octet to decimal, it's not going to equal 255. No, it's not going to equal 255 when you convert the whole thing to decimal. Jarvis asks, is the subnet mask in this scenario 255, 255, 255, 192? You got it. Great job. Wait a minute. The subnet mask in this scenario, forget this illustration I did here. That was just an aside. The subnet mask in this scenario is 255, 255, 255. We borrowed 1 bit, so it is 128. Do you see that now, Jarvis? We borrowed 1 bit. So the subnet mask is 255, 255, 255, 128. We borrowed 1 bit, which allowed for the creation of 2 subnets, which left 7 bits for host addressing, which gives us 126 hosts per subnet. Jarvis, I'm going to want you to type in confirmation that you can see that clearly now. If not, we'll go over it again. All right, awesome, he's got it. All right, perfect timing for our 15-minute break. When we get back, we are going to build upon this knowledge in order to actually see subnetting at work. You're going to love it. Have a great break, everybody.